Multi-area OSPF2 and OSPF3 with a stub area. This topology, the routers iOS 15.2 serial 0, serial 0, serial 1 to serial 1, in my case this will be serial 2 and serial 0. Use a simple Ethernet switch here, another here for gigabit interfaces. Gigabit interfaces needs a connection to another device. Otherwise, gigabit interfaces cannot be completely enabled. Gigabit 00. Okay, and remember iOS 15.2. Apply the following configurations to each router. Okay, also the hostname. Start all devices. R1. Configure terminal. Right-click hostname R1, R2. Configure terminal. Right-click to paste hostname R2, R3. Configure terminal. Right-click to paste hostname R3, R4. configure terminal, right click to paste, R4, configure the addressing and serial links, R1, okay, on R1 gigabit 00 and serial 0. Configure the IPv4 addresses and IPv6 addresses. All this interface serial 0 in my case is interface 30. Any clock rate, no shutdown. R2, okay, on R2 gigabit interface serial 0 and serial 1. Serial 0 in my case 30. This is the connection to R1. Serial 1, in my case, serial 3.1. The connection to R3. Okay, clock rate not shut down. R3 gigabit serial 1 and serial 010, in my case serial 32. R3 serial 1 gigabit 0 and serial, in my case, 32. Serial 1, the connection to R2. Serial 32, in my case. Three-two is the connection to R4. Finally, R4 serial 0 and gigabit interface. Serial 0, the connection to R3 and gigabit interface. Serial 3.0 gigabit 00. (2001) DB8 99 1 and 1. Okay. This subnet on R4 gigabit 00. First IP for gigabit 00. Link local address is not here, but configure anyway. Okay, exit. Enable unicast IPv6 routing. Create a static route to reach the subnets on R1, R2, and R3 using this NetsHub IP address R3. Okay, on R4 create the static route to reach the subnets on R1, R2, and R3 using the NetsHub IP address on R3. And finally create the static IPv4 route to reach other networks using the NetsHub IP address on R3. Okay, enable IPv6 unicast routing on all the routers. R1, that's it. IPv6 unicast routing. R2, that's it. IPv6 unicast routing. R3, exit. IPv6 unicast routing. R4 already configured with the unicast routing for IPv6. Use show IP interface brief and show IPv6 and show IPv6 interface brief. for example, from R1, ping all devices using IPv4. Okay, go to R1 and show IP interface brief. Okay, gigabit 0 and gigabit and serial 0. Ping to R2 serial 0 2.2. Success. Ping R3 serial 1 4.2. Okay, obviously it will not work because you need to implement a dynamic routing protocol like OSPF version 2. Okay, go to R2 and show IP interface brief. Gigabit 0, serial 0, and serial 1. Ping to R3 serial 1. Success. Go to R3. Show IP interface brief. Gigabit 0, serial 1 and serial 2. Ping to R4 77.1. Success. The same process using IPv6 R1. Show IPv6 interface brief. Okay, gigabit 0 up, serial 0 up. Ping to R2. Two. Success. Go to R2. Four, 2. Okay. Show IPv6 interface brief. Okay, gigabit, serial 0 and serial 1. Go to R3. Show IPv6 interface brief. 3 interfaces, gigabit 0, serial 1 and serial 2. Ping to R4. $77.1. Success. Configure multi-area OSPF version 2. Process 1 routers R1, R2, and R3. Configure the OSPF router ID on each router. Enable directly connected networks into the OSPF process using the IP OSPF process ID area and area ID interface command that is available with Cisco iOS version 2.3 and later. The show IP OSPF command should be used to verify the OSPF router ID. If the OSPF router ID is using a 32-bit value other than the one specified by the router ID command, you can reset the router ID using the clear IP OSPF, process ID, process command, and re-verify using the command show IP OSPF. Configure R3. Okay. Configure terminal router OSPF process 1, router ID 3, exit. Now configure two interfaces, gigabit 00 and serial 1. Interface gigabit 00, IP OSPF 1 area 0. Okay, exit. Interface serial, in my case, serial 31. Okay, 31. Also on OSPF process 1 area 0. Exit. Okay. Remember, both interfaces on R3, serial 1 and gigabit 00 placed on area 0. Gigabit and serial on area 0. Okay, R2. Okay, R2 is an area border router for area 0 and area 51. Okay, R2 is placed between area 0 and area 51. Area border router. Configure terminal router OSPF1, router ID, exit. Serial 0 on area 51. And gigabit and serial 1 on area 0. Serial 1, 31 in my case, IP OSPF1 area 0. Exit. Okay, the neighbor adjacency with R3. Okay, this is the router ID from R3. The neighbor on area 0. Okay, R3. Neighbor on area 0. Gigabit 00. IP OSPF1 area 0. Exit and configure serial 0, 30 in my case on area 51. Process 1 area 51. Exit. Configure R1, all interfaces on area 51. R1 gigabit and serial interfaces on area 51. Router OSPF process ID 1, router ID, exit, serial 0, 30 in my case, IP OSPF1 area 51, exit, and gigabit 00, also area 51 exit. Okay, verify. For example, on R2, and show IP OSPF neighbor R3 and R1. My local interface serial 31 to reach to connect R3 and serial 30 to connect R1. Show IP route, for example, on R3 and show IP route. Okay, this network 10 is an inter-area OSPF network. 10 is placed on gigabit on R1. Inter-area OSPF20 placed between R1 and R2. 30 OSPF in the same area on gigabit on R2, and directly connected networks, 3 directly connected networks on R3. Serial 1 gigabit and serial 010, in my case, serial 32. Very good. How many OSPF intra-area routes are in R3's IPv4 routing table? And how many inter-area routes are in R3's IPv4 routing table? R3 has one intra-area route in area 0. Is this 192.168.3.024, and 2 inter-area routes which are in area 51. These two, 192.168.1024 and 192.168.2030. Okay, R2 routing table. Show IP route. This OSPF network 10 placed on R1 on gigabit interface, 3 directly connected networks on R2, gigabit interface and 2 serial interfaces, and 1 OSPF route 5.0 placed on R3. Placed on gigabit 00 on R3. And why doesn't R2 have any inter-area OSPF2 routes in its routing table? R2 is an area border router, ABR, and has interfaces in both area 0 and area 51. So these networks are considered intra-area OSPF networks. Configure IPv4 default routes. On the autonomous system boundary router R3, forwarding traffic to R2. Propagate the default routing into OSPF version 2. They go to R3, configure terminal. The IP route, the default route use the NetHub IP address to reach remote networks. NetHub IP address on serial interface on R4 77.1, and go to router OSPF process ID 1 and propagate the default route, default information originate. Exit. On R3, verify and show IP route. This is the default route. Okay, and for example, go to R1 and verify the propagation and show IP route. Okay, this is the default route to reach internet or remote networks. Also on R2, show IP route, space, and the default route. Now configure IPv4 static route on the autonomous system boundary router R3 for the 192.168.99.024 network on R4. Redistribute the static route into OSPF version 2 using the redistribute static subnets command. The subnets parameter is used to include subnets and not just the classful network addresses. The redistribute command is discussed in more detail in later chapters. Okay, on R3, create a static route and propagate the static route on OSPF. Go to R3, configure terminal IP route, okay, this network 9090, okay, this network placed on R4 9090, and the NetHub IP address serial interface on R4 77.1. Go to router OSPF process 1 and redistribute static, and do not use classful, use the subnets. Classless. Exit. Go to R1 and verify. Show IP route. Okay, look at this. Okay, OSPFv2 OSPF external type 2. The default route is also E2, but it uses this character for the default route. Okay, go to R2. Okay, the exterior type 2 on OSPF. What does the E2 for the default route and the redistribute external route signify? Both routes are external type 2 routes. By default, external routes redistributed into OSPF are E2. The cost of a type E2 route is always the external cost, irrespective of the interior cost reached the network. Look at this, for example, on R1. The cost is 1 for the default route and 20 for the E2. R2 cost 1 for default route E2 and 20 for E2. go to R3 and show IP route. The default static route, the cost 0. The static route, the cost 0. Configure an OSPF version 2 stub area under the OSPF version 2 process on R1 and R2. Make area 51 stub area using the area stub command. The adjacency between the two routers may go down during the transition period, but it should come back up afterwards. Okay, R1 and R2. Configure terminal router OSPF process 1 area 51 stub exit. R2 configure terminal router OSPF1 area 51 stub exit. Okay, R1 and R2 on area 51 stub area. Okay, and okay, verify. Go to R1 and show IP OSPF neighbor. Okay, R2 is the neighbor. Go to R2 and show IP OSPF neighbor. OSPF neighbors R3 and R1. Issue the show IP route OSPF command on R1. Notice that R1 still has a default route pointing toward R2, but with a different cost than it had prior to being configured in a stub area. This is not the default route propagated by the autonomous system boundary router R3, but the default route injected by the area border router of the stub area. Also, R1 does not receive any external routes, so it no longer has an external network 192.168.99.0.24 in its routing table. Stub routers continue to receive inter-area routes from area 0. Okay, on R1, verify, show IP route. Okay, the default route injected by area border router of the stub area and no network 192.168.99.0. Look at the cost for this default route, 65. Go to R2, show IP OSPF. Show IP OSPF command, router ID 2, process ID 1. Okay, this is a area border router because it has area backbone 0 and area 51. What are the advantages of having a router receive a default route rather than a more specific route? A router memory and processing are conserved because the router has fewer routes to contend with. Why do all routers in a stub area need to know that the area is a stub? Routers need to know that an area is a stub for consistency so that no routers generate type 5 all-SAs or other OSPF features, such as virtual links, in an area in which they cannot exist. Configure a totally stubby area. A modified version of a stubby area is a totally stubby area. A totally stubby area border router only allows a single default route from the backbone, injected by the area border router. To configure a totally stubby area, you only need to change the command at the area border router R2 in this scenario. Under the router OSPF version 2 process, you will enter the area 51 stub not summary command to replace the existing stub command for area 51. The not summary option tells the router that this area will not receive summary inter-area routes. To see how this works, issue the show IP root OSPF command on R1. Okay, go to R1, show IP root OSPF. Okay, notice the inter-area routes in addition to the default route generated by R2. Inter-area routes and the default route generated by R2. Show IP OSPF database, show IP OSPF database. Okay, on R1, router link states and summary net link states. On R2, show IP OSPF database, router link states, summary net link states, router link states, summary net link states for area 0 and area 51, and type 5 autonomous system external link states. Okay, on R2, configure terminal router OSPF process 1 area 51 stub no summary. Enter and okay, go back to R1, show IP root OSPF, and you will have only default routes. Okay, notice that it shows only one incoming route from the area border router R2. The default route is injected by the area border router R2, and there are no inter-area OSPF version 2 routes and no external OSPF version 2 routes. On R1, examine the output of the show IP OSPF database command to see which routes are in area 51. You may need to clear the OSPF version 2 process to reset the entries of the OSPF link state database. Clear IP OSPF process. Yes. Okay, show the IP routes, the routing table with OSPF only the default route, the database show IP OSPF database. Okay, router link states and the summary net link states. Only the default route injected by R2. What are the advantages of making an area totally stubby instead of a regular stub area? What are the disadvantages? By making an area totally stubby, routers in area only see intra-area routes and a default routes. This can save a lot of router memory and processor time. However, as with any type of route aggregation, the loss of routing detail makes it possible for a non-optimal route to be chosen. Why did only the area border router need to know that the area was totally stubby rather than all routers in the area? The area border router is the gateway to the rest of the area and therefore is the boundary that all inter-area link state advertisements need to pass through. Because of this, it only needs to filter the type 3 link state advertisements and let the default route through. Okay, finally, ping from R1 to R2, R3, and R4. From R1 ping to R2, ping to R3, for 2, and R4, 77.1, success, and finally gigabit interface on R4, 99.1, success. Okay, go to R2, show IP route, R3, show IP route, very good. Configure multi-area OSPF version 3. Traditional OSPF version 3 implements OSPF routing for IPv6. In our dual stack IPv4 IPv6 environment, we have previously configured OSPF version 2 for routing IPv4, and now we will configure OSPF version 3 for routing on IPv6. OSPF version 3 messages are sourced from the router's IPv6 link local address. Earlier in this lab, IPv6 global unicast address and link local addresses were statically configured on each router's interface. The link local addresses were configured to make these addresses more recognizable than being automatically created using EUI64. Issue the show IPv6 interface brief command to verify global unicast address and link local addresses on the router's interface. For example, on R1, show IPv6 interface brief on gigabit 00 link local and global unicast addresses. Serial 3 IPv6 routing is disabled by default. The Cisco iOS version used with the routers in this lab has IPv6 Cisco Express forwarding enabled by default once IPv6 routing is enabled. To enable IPv6 routing, use the IPv6 unicast routing command in global configuration mode. Use the show IPv6 Cisco Express forwarding command to verify whether IPv6 Cisco Express forwarding is enabled. If you need to enable IPv6 Cisco Express forwarding, use the IPv6 Cisco Express forwarding command. For example, on R1, configure terminal IPv6 unicast routing and verify show IPv6 CEF Okay, very good. R2, configure terminal IPv6 unicast routing, and R3, configure terminal IPv6 unicast routing. Configure the OSPF version 3 process on each router. Similar to OSPF version 2, the process ID does not have to match other routers to form neighbor adjacencies. Configure the 32-bit OSPF router ID on each router. The OSPF version 3 router ID uses the same process as OSPF version 2 and is required if there are no IPv4 addresses configured on the router. R1. Configure terminal IPv6 router OSPF process 2 router ID 1 exit and configure on interfaces. On gigabit interface IPv6 OSPF process 2 area 51 exit and serial 0 30 in my case, also on 51 and exit. Remember, both interfaces on R1 are placed on area 51. Go to R2, IPv6, router OSPF process 2, router ID 2, exit the interfaces, okay. R2, 2 interfaces on area 0, 1 interface on area 51. Okay, interface serial 31 in my case, IPv6 OSPF process 2 area 0 exit gigabit 00 also on area 0 exit and serial 0 in my case serial 30 on area 51. Process 2 exit. Finally, R3, both interfaces on area 0. Do not configure the serial 010 in my case serial 32. Do not configure this interface on OSPF. Only these two interfaces placed on area 0. R3, IPv6, router OSPF2, router ID 3, exit, gigabit 00, IPv6, OSPF, process 2, area 0, exit, serial 1, in my case serial 31, placed also on area 0, process 2, exit. Okay, for example, on R2, verify the neighbors show IPv6 OSPF neighbor. Okay, success both R3 and R1. The routing table, for example, on R2, show IP OSPF, show IPv6, root OSPF. Okay, the remote networks on R2. Okay, the remote networks on R2 are subnet number 1, CCNPv7, and another remote network is CCNPv5. Okay, the LAN interface on R3. Okay, very good. And for example, on R1, and show IPv6 root OSPF. 3 remote networks on OSPF, inter-area OSPF 3, 4, and 5. Okay. For R1, the remote networks on OSPF are 4 between R2 and R3, 5 on gigabit on R3, and 3 gigabit on R2. On R3 and show IPv6 root OSPF. The remote networks on R3 are 2 inter-area 1 and 2. Okay. Both routes placed on area 51. One on gigabit on R1 and 2 between R1 and R2. And intra-area 3. Okay, 3 placed on area 0 on gigabit interface on R2. Configure an IPv6 default route on autonomous system boundary router R3, forwarding traffic to R2. Propagate the default routing into OSPF version 3. Okay, go to R3, IPv6 route, configure terminal, IPv6 route, the default route, the NAT hub IP address, okay, the NAT hub IP address is IP address of serial interface on R4, 77 column 1, and propagate IPv6 router OSPF process 2 default information originate, and configure an IPv6 static route on the autonomous system boundary router R3 for the 99.1 prefix on R4. Redistribute the static routes into OSPF version 3. Configure terminal, IPv6 route, (99.1) column prefix 64. Is this network on gigabit on R4? And the NAT hop IP address 77 colon colon 1. Redistribute IPv6 router OSPF process to redistribute static exit. Okay, finally verify and show IPv6 route. Okay, the default route and the static route. R2 show IPv6 route. The default and the static. R1 show IPv6 route. The default and the static. Configure an OSPF version 3 stub area. Configuring stub areas for OSPF version 3 is similar to that for OSPF version 2. The stub area functionality is the same for OSPF2 and 3. Under OSPF 3 process on R1 and R2 make area 51 a stub area using the area stub command. R1 configure terminal IPv6 router OSPF2 area 51 stub exit. Go to R2 configure terminal IPv6 router OSPF2 area 51 stub exit. Okay, verify and on R2 show IPv6 OSPF network. Okay, but networks R3 and R1 success. To verify that the stub area functionality is the same in OSPF3 as OSPF2, issue the show IPv6 route OSPF command on R1. Similar to OSPF version 2, notice that R1 still has a default route pointing to R2 but with a different cost that it had prior to being configured in a stub area. Again, this is not the default route propagated by the Autonomous System Boundary Router R3, but the default route is injected by the area border router of the stub area. R1 also does not receive any external routes, so it no longer has the 99.1 prefix in its routing table. Stub routers continue to receive inter-area routes. R1 and show IP route OSPF. Okay, only the default route with a different cost. Okay, before the cost for the default route was 1, now is 65. Show IP route, okay, space 65. Only the default route. Configure a totally stubby area. A totally stubby area border router only allows in a single default route from the backbone injected by the area border router. Configuring a totally stubby area, you only need to change the command at the area border router. R2 in this scenario. Similar commands used to configure a totally stubby area for the OSPF version 2 process are used for OSPF version 3. Okay, first of all, verify on R1 show IP root OSPF. Okay, the default route for the stub area and 3 and additional 3 inter-area OSPF routes. Go to R2 and configure the totally stub area. Configure terminal IPv6 router OSPF process 2 area 51 stub no summary. Verify again on R1 show IPv6 route OSPF, and there is only the default route. On R2 and show IPv6 OSPF. R2 is the area border router because it has backbone 0 and 51. For area 51, it is a stub area, not summary link state advertisement. In this area generates a stub default route with cost 1. What is meant by the highlighted output for area 51? R2 has a single interface that is member of area 51. The stub not summary indicates that this is a totally stubby area. Generates a stub default route means that R2, the area border router, is generating the default route received by the internal routers such as R1. It is not the default route advertised by the autonomous system boundary router R3. Thank you very much.